complex. So I think in the previous session, I was giving you some introduction to complex number system. Complex number is cannot be treated exactly as a number. It is in fact a point in a Cartesian plane, which we call it as the Argand plane. Okay. Now take some notes. Complex function. Complex function. Complex function. Let capital D be a domain of the Argand plane. Capital D be a domain of the Argand plane. Let W equal to f of z be a function from D to C. It means it's some kind of a function from D to C, the domain D to complex plane. Then f of z equal to u of x comma y plus iv of x comma y, where z equal to x plus iy, is called complex function. Now, it quite obviously, if you have a complex plane in which I take a domain D, which is mapped by a function f to another complex plane. Okay. So points of here would be mapped to points in the complex plane here. Generally, both of them are complex planes by itself, but for our convenience, we treat this as Z plane and we treat this as W plane, in which this is U and this is V. Okay, UV plane or W plane. So W equal to U plus IV becomes our complex function. Okay. Limit of a function. Limit of a function. Take a note. I think I assume that everyone knows what is the limit and what is continuity, what is differentiability. In calculus, our real calculus, wherein we had all a real number system there. Right now we are talking about complex number system, in which I am talking about complex functions, and these functions having limits, continuity and differentiability at certain points. Okay, take this one, limit of a function. Let W equal to f of z. Let W equal to f of z be a function defined in a domain D. Be a function defined in a domain D of the Argand plane. We say that f of z tends to a limit L as z tends to a, in brackets, along any path in D. Just write it down, I will explain it anyway. Along any path in D, if given an epsilon greater than 0, there exists a delta greater than 0 such that mod f of z minus L less than epsilon whenever mod z minus A less than delta. This is symbol for there exists. Did I mention at any point of time? There exists delta. In fact, this is epsilon. There exists delta such that whatever. Okay. This is in fact a classical definition of limit. We call it as a classical definition of limit. And this is how a limit definition is formed basically. What it says finally is, of course you can have, then we write limit z tends to a f of z equal to L. Z tends to a f of z equal to L. Okay, let me give you synopsis of what you already know in real calculus, and then I will try to relate it with our complex calculus. I am talking about xy plane. Okay, suppose y equal f of x is a function, a curve is a curve. What we say is the limit for the function f of x at x equal to a exists if the left hand limit equal to right hand limit. What is the left hand limit and what is the right hand limit actually? Left hand limit means if you consider a delta neighborhood of a, suppose here to here, this we call it as a minus delta, this is a plus delta. If I start from this point and try to approach a from left hand side of a, I start at some point in the delta neighborhood of a and try to approach a as x tends towards a from left, as x tends towards a from left, we write like this. It's a symbolic notation, it's not a power minus, nothing. A minus stands for from left hand side of a. If I start approaching a, then what happens to the value of the function f of x? Suppose it is equal to L. Then we say that left hand limit of the function is equal to L. Similarly, if you start from right hand side and start approaching a, limit x tends to a plus f of x is equal to exactly equal to L suppose. That means from the left hand side, whatever the limit that we have is exactly equal to the right hand side limit, then we say the limit exists. Okay, this is what is delta neighborhood. Okay, now what happens here is if x is moving in the neighborhood of a, delta neighborhood of a, then there will be some f of x which also moving in some neighborhood. If it is epsilon neighborhood of L, instead of z you treat it as x. Instead of z, if you treat it as x, we are in real plane then. Okay, we are in real plane. If x is, this is also x is moving in the delta neighborhood of a, if x is moving in the delta neighborhood of a, then if f of x is also moving in the epsilon neighborhood of L, that means f of some value, whatever the value of the function that you are getting as you are moving from the left hand side or you are moving from the right hand side, if it is exactly equal to L, the height, I am talking about height L, okay. If both of them are equal, we call that limit exists. Of course, if this exactly equal to f of a, that means left hand limit equal to right hand limit, the limit exists and equal to f of a, then we say that the function is continuous at x equal to a. That's what we learned in our +2 level or whatever. Now, if I say f of a, then somewhere or the other my function this becomes my f of a. Not necessarily every time L should become equal to f of a. Left hand limit equal to right hand limit is possible, but may not be exactly equal to f of a. Not necessary always. That means limit might exist, but it might not be a continuous function at x equal to a. I'll give a very simple example. Generally, I give the same example every time. Suppose tomorrow you become an IAS officer. You become an IAS officer. Okay, so you have right now maybe a collector of some district. Okay. Now, suppose you have Indian level union government some scheme wherein you have to construct a lot of road connectivity to even remote villages also. Suppose. Now, once you have to construct roads, now you'll always be going for a bidding, tenders, okay, and then someone comes and constructs a road. You are given someone to construct the road and he constructed the road. But one day or the other you have to go and inspect the road. Suppose there is a village A and another village B is there, and you have to construct a road between A and B. And someone constructed the road. You have to go and inspect the road, whether it is properly constructed or not. Okay? Now, how to inspect it? There are different ways of inspecting the road. One is, you go to village A, from A, travel towards B, along the road, and if that road takes you to village B, you say that there is a continuous road that is laid between village A and village B. That is one way. Second way is, you directly go to village B, start moving on the road towards village A. If you are able to reach A, then I can say that there exists a continuous road that lies between B and A. Another approach is there. You are a collector, you can ask your deputy also. You start from A, you ask your deputy to start from B. Both of you travel along the road, one from this side, the other from this side. Both of you meet on the road, f of A. Both of you meet on the road, function f of A. Then definitely I can say there exists a continuous road, continuous line, continuous curve that exists between A and B. Suppose, that means left hand limit equal to right hand limit equal to exactly equal to f of A. There is another possibility is there. You start from A, you go like this, B also comes like this, both of you meet here. Left hand limit equal to right hand limit, but is not equal to f of A. Left hand limit equal to right hand limit. Both of you are meeting at some point, but where you are meeting? You are not meeting on my curve. You are not meeting on my curve. Therefore, my curve I cannot say it is a continuous curve. It might be that this curve is a continuous curve. I am least bothered about that curve. I am bothered about my curve, my f of x curve. If my f of x has to be continuous at x equal to a, then not only left hand limit should become equal to right hand limit, both of them should be equal to f of a exactly. Only then I can say my function f of x is a continuous function. Or else some other f dash of x is a continuous function. I am least bothered about f dash of x. I am just bothered about my f of x. So you have to meet on the curve, left hand limit equal to right hand limit equal to f of a, only then you can say my curve is a continuous function, right? అంటే ఇట్లాంటి ఇనేసి వదిలేయాలన్నమాట, ఎక్కువ ఆలోచించుకోదు వాటి గురించి, అదే టైం పాస్ చెప్తుంటాం కొన్ని. ఓకే, సో వాట్ ఎవర్, the same concept we apply to complex functions as well. Now, but here there is an extension of our real variables. In real analysis, what happens is, there is only f of x, f is a function of x alone. F is a function of x alone. Now, what happens if f is a function of x alone? It is only x which is moving in the neighborhood of a. That means you can have a left hand limit or you can have a right hand limit. Only two limits are possible. Either to reach A, you can reach from left hand side, or you can reach from right hand side. Left hand limit is possible, right hand limit is possible. But if you see this function f of z, z in fact is a function of x and y. Your f of x function would be a function of x as well as function of y also. There are two things which are changing. There are two independent variables, x and y. X is changing as well as y also is changing now. Now what happens? Suppose this is a point. Suppose I talk about a comma b is the point, or z equal to a plus ib is the point at which my complex function, whether it is continuous or not, if I am trying to check here, what happens? X will be moving in the neighborhood of a, y will be moving in the neighborhood of b. So x moving in the neighborhood of a means from left it can move towards a, from right also it can move towards a. What about y? Y can move from top limit or bottom limit. Both of them are moving. X is changing, y also is changing. Then there is a possibility that you can have this limit, this limit, this limit, this limit. So many limits can be there. It's not just two limits or four limits. It's all about infinite number of limits are possible. That means to reach the point a comma b, there are infinite ways of reaching the point a comma b. It may not be only straight line. You can move even along a curve also. So many paths along any path indeed to reach the point z equal to a. Are you getting? So in complex analysis, your function not only depends on x, it also depends on y. When x is changing, your function is changing. When y is changing, your function is changing. If both of them are changing, again your function is changing. How many ways that it can change? Infinite number of ways. So it's not about left hand limit or it's not about right hand limit being equal. It's top limit, bottom limit, this limit, that limit, any limit you consider. You travel through any path to approach the point a comma b. All the limit values have to be same. So all these infinite number of limits that you have, each limit you have to calculate, each limit value have to be same. Then only I can say limit exists. Are you getting? If at least one of the limits is different from the rest of them, then limit do not exist. Forget about continuity. Continuity comes later. Continuity comes later. First you need to have that limit. To have that limit, it's not about left limit or right limit, top limit, bottom limit. You travel to any path. Any path you travel and try to approach the point a comma b. All the limit values have to be same. Every limit, not even single you can leave it. Okay? Every limit value have to be same, then only the limit exists. If one of the limit value is different from the others, the limit do not exist. Forget about continuity. Continuity anyway will not be there. Right? That's what complex limits all about. So you just can't check only left limit or right limit, or you just even can't check about one path. All infinite number of paths you have to check. So which is not practically feasible actually. Checking all those infinite number of paths is not at all feasible. So saying that the limit exists is a very difficult affair. But to say limit do not exist is very easy. If you have any function f of z, at some point z equal to 0, if you have to say the limit do not exist is very easy, because if I can identify two paths, travel to two paths and try to approach z equal to 0, limit value of one path, limit value along another path, if two are different values, then the limit do not exist. It's very easy to say that. But saying that the limit exists is a little bit difficult affair. You have to really use this complex concepts or reanalysis concepts, and this classical definition really works out there. If you see this classical definition, whenever z is moving in the delta neighborhood of a, f of z is moving in epsilon neighborhood of L, then I say limit z tends to a, z tends to a, f of z equal to L. If this L equal to f of a, then it is continuous also. Right? If L not equal to f of a, limit exists, but it is not continuous function. Is that clear? Any questions here? And the delta neighborhood, epsilon neighborhood, okay na? It's nothing but whenever in the real calculus, if I say when x is moving here, f of x is moving here. That's the point. Okay, in the epsilon neighborhood of L and delta neighborhood of L. All these things anyway you will study very, very deeper in real analysis. When madam comes into picture for real analysis, by the way, are you able to understand model algebra? అర్థమవుతుందా పక్కా అర్థం కానివి ఏమైనా ఉన్నాయా అంటే అర్థం కాకపోయినా మేడం అడగాలి నన్ను కదా అడిగేది ఓకే ఫైన్ టేక్ దిస్ continuity one more thing, even in real analysis also, not only one independent variable which we already discussed in our plus 2 level, two variable scenario also appears in real analysis. The concept is same. Here two variables, independent variables. Real analysis also you can have a context wherein you have two independent variables. We'll call it a multi-variable calculus in real analysis. Okay? There also this limits, continuity, differentiability will also be there. Anyway, I am discussing it here. That will be useful for your real analysis also. Continuity. A function w equal to f of z, a function w equal to f of z defined on a closed and bounded domain capital D, defined on a closed and bounded domain capital D, is said to be continuous at a point A, is said to be continuous at a point A belonging to D if limit z tends to A, f of z equal to f of A. Not only the limit exists, but the limit value has to be equal to f of A. Okay. Chinna concept, small concepts, try to understand them properly. Things become easy for you later. Next. A function f of z is said to be, a function f of z is said to be continuous in a domain D, continuous in a domain D if f of z is continuous at every point of D. A function f of z is said to be continuous in a domain D if it is continuous at every point of D. So earlier it was continuity at a point. Now this definition is for continuity in a domain D, means at every point in the domain D f of z has to be a continuous function, right? Differentiability. Differentiability. Now, what is the differentiability in real analysis? Differentiability in real analysis, if there exists a limit x tends to A of f of x minus f of A by x minus A. If the limit exists, that means if the left hand limit of this entire g of x, if g of x equal f of x minus f of A by x minus A, which in fact is nothing but, if I say this is A, suppose x is A plus delta or A minus delta, okay? This is suppose f of A, this is f of x coming from A plus delta. This can sometimes also can be written as limit h tends to 0 f of x plus h minus f of x by h, where x equal to A plus h is moving towards A, means h is tending to 0. if this is a plus h, from right hand limit if I consider, from x is moving from a plus h towards a, means that h is tending to 0, okay, which means that x becomes x plus h minus f of x by h, which in fact is nothing but the slope at this point. Initially, this is f of x plus f of x minus f of a. This is x minus a, which is equal to h. The ratio is x minus a, which is equal to h, which in fact is the gradient that we call, the slope that we call, comes into picture with this ratio, okay. As h is tending to 0 or x is moving towards a from the right side, this point actually moves here. This point actually moves here. Finally, this becomes a line, a slope. Okay, it becomes an angle basically, angle, which in fact we call it as tan theta or whatever, the gradient. If this limit exists, that is if the left hand limit equal to right hand limit, then I say my function f of x is differentiable function at the point x equal to a. I just need to have this limit. Similar context, limit z tends to a, f of z minus f of a by z minus a. If this limit exists means to approach the point A, you can travel through different paths. It's not about only left limit or right limit. Infinite number of ways that you can approach A. All the limit values have to be same. Then I can say my function f of z is a differentiable function at z equal to. Let w equal to f of z be a function defined in a domain D. Be a function defined in a domain D. F of z is said to be differentiable. F of z is said to be differentiable. Is said to be differentiable at a point A belongs to D. At a point A belongs to D, if limit z tends to a, f of z minus f of a by z minus a exists, limit z tends to a, f of z minus f of a by z minus a exists and is independent of how z approaches a and is independent of how z approaches a. That means independent of the path it chooses to travel towards a. If the limit values are same, then the limit exists. That means my function f of z is a differentiable function at z equal to a. Okay. Then we write the differential of f of z at z equal to a. Then we write the differential of f of z at z equal to a as f dash of a, as f dash of a. And there are certain things, certain concepts which you already know, which I don't want to go deeper into that. One thing that we know is when a function f of z is differentiable at a point z equal to a, then we already know that it is continuous at z equal to a, but the converse is not true. The converse means if f of z is continuous at a point z equal to a, then it may not be differentiable at z equal to a. Last one. Differentiability implies continuity. Differentiability implies continuity, but not conversely. But not conversely.